Hello class. Today we're going to look at is how to do a chi-squared goodness of fit test on Excel. So Excel doesn't have any sort of built-in chi-squared goodness of fit or independence tests like they do with many other type of tests in the data analysis pack. But we can create our own template that does it for us. So let's start with a little example as to what we would actually use the chi-squared test. So we have this prompt: a local restaurant in Moore Park tracked the purchases of their customers for 1 year. They found that 25% of their sales were burgers, 16% were pastas, 20% were salads, 12% were sandwiches, 16% were pizzas, and 11% with hot dogs. They just opened a new location in Thousand Oaks and found that in the first week they sold 132 burgers, and you see the numbers for each of the other purchases. And the question is, does this provide sufficient evidence at the alpha equals 0.05 level to conclude that the Thousand Oaks orders follow a different distribution? And so this is an example of a time where we're going to use the chi-squared goodness of fit test. And I ask, well, what is the chi-squared goodness of fit test? Well, a chi-squared goodness of fit test is when you have some sort of hypothesized proportions where there's going to be more than two, because otherwise we could just use a one prop z test if there were only two categories. But if you have three or more categories and you want to say, does the overall distribution differ, then you're going to have to use the chi-squared goodness of fit. Now you could do a bunch of individual one prop z tests on each individual proportion. The problem with that is that every time that you do that, you have a chance of a type 1 error, and then you'd have to sort of adjust what the p-value would need to be. Whereas the chi-squared test of independence sort of takes those all into account at the same time, and it answers the question of, does the overall set of observations differ from the hypothesized values by enough that you can't really explain it by random sampling error, or that it would be very rare for it to be explained by random sampling error. And so we're not going to be using the normal distribution or the t-distribution anymore. Instead, we're using something called the chi-squared distribution. And something to notice about the chi-squared distribution, which is different than the normal or t-distributions, is that it's no longer symmetric. We see that it's skew right. Another property that it has is it doesn't have positive and negative values. It only has positive values. Notice it starts at 0 and goes off to infinity. And so what it does is it basically, the larger the chi-squared statistic means the greater difference that we have between our observed values and our hypothesized values. No difference would be a chi-squared of 0, and the larger the difference is, the larger the chi-squared statistic. And because of that, we're always going to use the right tail of the distribution, because it's a question of what is the chance of getting something that differs from the hypothesis by at least as much as how our data differed. And so the way that the null and alternative hypotheses will always be stated is that the null hypothesis will always be something of the form: the proportions are equal to some sort of hypothesized collection of proportions. In this case, it's this hypothesized collection of proportions. And then the alternative is always going to be that at least one proportion is different. It might be that they're all different, but it could be that some are the same, but some are different. And that would make it so that it would be different overall. All right. So let's set up actually figuring out how to compute this. So once we have in our observations and our expected values, the first thing we want to do is figure out, well, how many observations did we make? So we can type in equals sum, and collect all the observations that we got. And we have 478 observations here. And I'm actually going to drag this to the other columns because we're going to want to add up all the other columns as well. Now the expected proportions add up to 1, as they should. Now note you could have the proportions add up to something slightly different than 1 if you have rounding error. And we'll actually talk a little bit about how to account for rounding error. Now the expected number, well, if you have the expected, you just say, okay, well, I take the number of observations. And something that we're going to do here is when I copy and paste this value, I'm always going to want to refer to the same number of observations, 478. And because of that, I will then put dollar signs on the B and the 13. And that way this cell gets fixed. And so every time that I calculate the expected value, I'm going to refer to this same 478. And so the value that you get is just the total in your sample size multiplied by your proportion. And so I will not put dollar signs on here because I want to copy and paste this down and use the different proportions for each row. All right, and so then I copy and paste down, and notice the total of the expected number is the same as the total of the observed, and so that's really nice. One thing that you could do if this added up to say like 0.99 or 1.01, just to make sure that the expected number always is the observed number, even if this is a tiny bit off from 1, is you could always just divide by this value. And I'll put dollar signs because we want this, because this value is going to be fixed as well. And notice it won't change anything here because I'm just dividing by 1. But if I had something that was slightly off, like let's say this was 0.12, notice now the expected proportion is a tiny bit off of where it should be, but the expected number still stays where it should be at 478. All right, so I'll put this back at 0.11. And so now the next thing we need to do is find the chi-squared statistic. And so the chi-squared statistic is you just take the number observed minus the number expected, you square it, and you divide by the number that is expected. So this would be parentheses, the number observed minus the number expected. You square it and you divide by the number expected. And this sort of tells us overall what's the difference from expectations. So we see the difference from expectations is the numerator. You square it so that a positive difference or a negative difference, those wouldn't cancel out. And then you also divide by the expected because, say, if you expect 100 and you're off by 5 versus if you expect 5 and you're off by 5, then you'd have very different sort of differences from expectations in that sense. And so then we can copy and paste this down, and we get the overall difference from expectations is this number 5.9. You might say, well, what is this 5.9? Well, we're going to use it in the chi-squared distribution. All right, so for the chi-squared, I'm just going to say equals and then sum, and I'm just going to grab this whole column. All right, and we again get that same 5.905. Now the degrees of freedom is always one fewer than the number of categories. So I can just put in count, and then it doesn't really matter which row or column I put in. And then I subtract 1, and there we go. So the degrees of freedom is 5. Now here's the important part, is to get the p-value. And so the p-value would be equals and then chi-sq dot dist for chi-squared distribution. And then we're going to do dot rt. So remember, in previous examples, the chi-square, or with the normal distribution or the t-distribution, the default is to use the left tail. And that's how it is with the chi-squared dist, is to use the left tail. Since we want the right tail, we're going to do chi-squared dis dot rt to get the right tail. And so there's our chi-squared value. Then we need to input our degrees of freedom. And then we can close that, and we get a p-value of 0.316. And so to answer the question here, since the p-value is greater than the significance level, we do not have evidence to suggest that the proportions are any different than they were in Moorpark. All right, so we do not reject the null hypothesis. The values, the observed proportions, are consistent with the hypothesized proportions. All right, and so you could say that the difference between the sales at Thousand Oaks is not significantly different than those that were sold in Moorpark. That any sort of differences could be just a result of random sampling error. So we see that, yeah, we sold a few more burgers than expected. We sold some more hot dogs than expected. Something had to have been lower. It looks like we didn't sell as many salads as expected. But all these numbers are fairly close to expectations, and so the overall difference from expectations is not statistically significant. Now there's one other thing that I wanted to talk about, and that's the critical value. And so to get the critical value, which a lot of the questions on the homework in Pearson ask about finding the critical value, well, that would just be that we would want the value that the right tail is equal to the significance level. And so we can do equals, and then chi-sq dot inv, because we're going to do the inverse, dot rt, because again we're looking at just the right tail. And then we have the significance level, we have the degrees of freedom, and there we go. So we have a critical value of 11.07. So again, we see the chi-squared is, in this case, not as great as the critical value. So a chi-squared statistic of more, so this means that a chi-squared statistic of more than 11.07 would be statistically significant. All right, so I realize it's a little bit opposite in terms of the p-value you'd want to be less than the significance level, but the chi-squared value you'd want to be greater than the critical value, in both cases to be statistically significant. And it's just sort of, you got to remember what p-values and critical values all mean. So the p-value is what's the chance of getting something more extreme than that if the null is true. So a small value would imply that the data would be very rare if the null is true. So that's statistically significant. Whereas the test statistic is how far are you from the hypothesis. And so a greater test statistic means that you are further away from the hypothesized values. And so that's why a large test statistic is going to mean statistically significant. And the critical value tells you the cutoff between statistically significant versus not statistically significant. And so I think that is a good place to wrap this up. And I hope that you are able to get everything done with the chi-squared goodness of fit test. Thank you.